Well, here's another problem, a bit of a challenging problem, and this is the method of Lagrange multipliers when we have two constraints, and I'll just show you by an example. If there are two constraint functions, g and h, introduce a second Lagrange multiplier, let's call it mu, lambda for L Lagrange and mu for M multiplier. So then we can say that del F equals lambda del G plus lambda del H. So here's an example, another difficult example from thermodynamics. The temperature at the point x, y, z in three-dimensional space is given as 20 plus 2 times x plus 2 times y plus z squared. And that's temperature on, here's a constraint, on the sphere. X squared plus y squared plus z squared equals 11. Sphere, center at the origin, radius square root of 11. And we're going to find the extreme temperatures on the curve formed by the intersection of the plane x plus y plus z equals 3 and this sphere. So where is this temperature highest and again lowest on this sphere with the intersection of this plane? Complicated problem. So here's how we start. Delta t, well, partial with respect to x is just 2, so 2i. Partial with respect to y is 2, so plus 2j. Partial with respect to z is 2zk. And if we make g of x, y, z equal to x squared plus y squared plus z squared minus 11, we can say lambda del g is lambda times 2xi plus lambda times 2ij plus lambda times 2zk. And mu times del h, if we make h of x, y, z equal to x plus y plus z minus 3, would just be mu times 1i plus mu times 1j plus mu times 1k. And so what we know from this is that since this del t equals lambda del g plus mu del h, we know that the I components are the same. So 2 equals 2 lambda x plus mu. That's where this equation comes from. We also know from the j component that 2 equals 2 lambda y plus mu. And we also know that 2z equals 2 lambda z plus mu. And of course we also have our constraint equations, x plus y plus z equals 3, x squared plus y squared plus z squared equals 11. So if we subtract this equation from this one, you should see that we'll get lambda times x minus y equals 0. Subtract this from this, we get 0. Subtract this from this, we get 0. We have 2 lambda x minus 2 lambda y, divide out by the 2, factor out the lambda, you got lambda times x minus y equals 0. And rewriting this third equation with the z's all on the same side, we got 2z times 1 minus lambda minus mu is equal to 0. And we also have our other two constraint equations. Now, either from this equation, either lambda is 0 or x equals y. So from this top equation, if lambda is 0, then this is 0 and mu equals 2z. Now if mu equals 2z and lambda is 0, then if we put that in here, actually you could put it in here also, it wouldn't matter, we would get 2z plus 0 equals 2, so z equals 1. And if z equals 1, then the last two equations, this one is now x plus y plus plus 1 equals 3, so x plus y equals 2. This one is x squared plus y squared plus 1 equals 11, so x squared plus y squared equals 10. Now, we can solve this system by substitution. If we substitute for x 2 minus y, so 2 minus y squared plus y squared equals 10, I have that worked out over here. You can see that y equals -1 or y equals 3 are the solutions for this equation if you factor it. So z equals 1 and y equals -1, then going to here, if z equals 1 and y equals -1, then x equals 3. But if z equals 1 and y equals 3, so back to here, if z equals 1 and y equals 3, then x equals -1, and we have these two critical points, 3, -1, 1, and -1, 3, 1. Okay? Now, that was under the consideration that, oh, I went too far, that lambda equaled 0, but another possibility exists that x could be equal to y. So if x equals y, then this equation becomes 2y plus z equals 3, and this one becomes 2y squared plus z squared equals 11. And so if we solve this one, let's say for z equals 3 minus 2y, and put that in here, then we get this equation. And if you take the time and trouble to solve this equation, you see we get this, which yields to this equation, and it's a quadratic, and trust me, after simplifying, you'll see why. I'm just going to solve, but you know how to solve a quadratic, so we get these two solutions. I would call this one 3 plus 2 squares to 3 over 3, the whole thing over 3. Same story with this one. So we got those two solutions, and from what that substitution yielded, and now that we've got those two, we can solve the fact that x equals y means that one of the solutions was this, and if that's x and y, then we need to see what z is, but recall z equals 3 minus 2y, so that means z equals this, which is simplifies as this. Trust me about that. You can work that out yourself. And keeping in mind, if we had this possibility, then z would be this answer right here. So what we've got 4 points. The two we got from here and the two we got earlier. This one is x and y both 3 plus 2 squares to 3 over 3, and z equal to 3 minus 4 squares to 3 over 3, and we also got x and y both at 3 minus 2 squares to 3 over 3, and z equal to 3 plus 4 squares to 3 over 3. So we've got these points, and we just evaluate them. And t at 3, -1, 1, you might not recall what t is, so let me go back and here it is, right here. This is our t. I'll paste it in right there. Right, oof, not a good place to paste it, was it? So if I go up here, move that down a little bit, but move this one back up a little bit, there we go. So there's our t, and if you put in x is 3, y is -1, z is 1, you do get 25. So that's 20 plus, that's 26 minus 2 plus 1. 26 minus 2 plus 1 is 25. So we get temperature of 25. And if you do the same thing with the point t equals -1, 3, 1, you also get 25. I'm not going to work you through that. I'm definitely not going to work you through this one and this one, but if you take the time to evaluate t, put in here this x there, this y there, and this z there, trust me, you'll get 30 1/3. Okay? I can evaluate that just using my software, but you can use a calculator and come up with that. And this will also give you 30 1/3. So the other possibility, this was x, this was y, this was z, gives you 30 1/3. Now what we've learned from this is, on the sphere's intersection with the circle, with the plane, the sphere x squared plus y squared plus z squared equals 11, and the plane x plus y plus z equals 3. this temperature is greatest at the point where x is 3 plus 2 squares of 3 over 3, y is 3 plus 2 squares of 3, and z is 3 minus 4 squares of 3 over 3, and that maximum temperature is 30 1/3. It's also maximum at this other point, and you can read through that if you want. But the temperature is minimum at x equals 3, y equals -1, and z equals 1 at 25, and minimum at -1 for x, 3 for y, 1 for z, also at 25.